Hello, my name is Lea Morath, and I'm a fourth-year biomedical engineering student. My research is in the area of biodegradable stent material, specifically at a 1-month time point. A little bit of background is that a coronary stent needs to maintain its structural integrity for around 6 months after implantation to allow for the healing and strengthening of the reopened artery wall. After this fact, a bioresorbable stent may be preferred over traditional permanent stent, as the stent could degrade and allow the artery to return to normal function and basal motion. Pure zinc has been found to be a desirous material for this application, as it remains in the artery for greater than 6 months before fully corroding. Zinc has also shown excellent biocompatibility, and it suppresses smooth muscle cell proliferation into the new intima or the new tissue formation around the implant. The new intima is a common cause of arterial occlusion, so if it could be smaller, it would be better. However, zinc lacks the mechanical strength needed for a stent, as a minimum of 300 megapascals is required. So to increase its mechanical strength, zinc has been alloyed with multiple metals, including silver, manganese, copper, and zirconium. Silver has been used in the past to coat implantable devices for its antibacterial properties, and manganese has been shown to increase tensile strength by refining grains. The alloys were also thermal treated in some instances, as thermal treatment can be used to organize grains and increase grain size. The methods used for this project is that 3 different wire types of zinc silver manganese, and zinc silver copper manganese zirconium compositions were implanted into the abdominal aortas of rats for 1 month. After this time, the samples were removed, cross-sectioned at 10 micrometers, and staying with H&E for general cell morphology information and Verhoef van Giesen, which was then quantitatively analyzed for base neointimal length, wire to lumen thickness, and neointimal area. In figure 1, you can see that the red line shows base neointimal length. The blue line is wire to lumen thickness, which is taken at the apex, and the green line shows the neointimal area, which excludes any corrosion product and the wire implant itself. Finally, the cross-sections were fluorescently stained with CD68 to look at macrophage infiltration and smooth muscle cell alpha-actin, and both were quantitatively analyzed for fluorescent signal. In figure 2, you can see graphs for average wire to lumen thickness, neointimal area, CD68 signal coverage, and alpha smooth muscle actin signal coverage. The normal or as received alloys are in gray, and the thermal treated alloys are in yellow. The black stars indicate significance of a p-value less than 0.05, and these significance values were determined using a student's t-test. I found that zinc, silver, copper, manganese, zirconium thermal treated had a significantly larger wire to lumen thickness and neointimal area than its as received counterpart. No significance was found between any alloys for base neointimal length. For CD68, zinc silver temp treated and zinc silver manganese temp treated both had significantly more CD68 signal coverage than zinc silver copper manganese zirconium. And finally, zinc, silver, copper, manganese, zirconium had significantly more smooth muscle coverage than its zinc, silver counterpart. In figure 3, you can see representative images of the 3 main quantitative stains of VVG, CD68, and alpha smooth muscle actin. In the latter 2 stains, the green stain is for the specific antibody, and the blue is a DAPI counter stain, which shows cell nuclei. The overall conclusions that I drew from my data is that the normal alloys perform better than the thermal treated ones in terms of neointimal size, which is the opposite of what was expected. And the addition of copper and zirconium in the third and final alloy decrease the macrophage infiltration and increase the smooth muscle cell infiltration. My future plan is to investigate if there are any differences in neointimal size or macrophage and smooth muscle cell infiltration between 1 and 6 months. Finally, I would like to thank the Michigan Space Grant Consortium and Pavlis Honors College for providing me funds for my project.